Okay. Can you hear me in the last row? Okay. Then let's start. Um, so that's fine, right? Okay. So yeah, I'm substituting today Georg. So this is the reinforcement learning lecture. My name is Andreas René Geist. I'm a postdoc with Georg, working mostly on physics-informed machine learning. And today I present to you model-free prediction. So yeah, what have you seen in lecture number 2? That was essentially you got introduced to known Markov decision processes. So that means you know the transition probabilities, the reward function, and everything was known, so you can compute essentially your value function. We also learned that we can essentially, if we have a Markov decision process, so decisions means we have to compute actions, we can reduce that if to a Markov reward process, an MRP, if we just follow the policy that we currently have. And this makes things simpler, just also notation-wise, but also in deriving equations. And then we saw different methods for estimating the value function and also evaluating the predominant. So first of all, policy evaluation, and then we did control. So we had to choose actions, and this we did with policy iteration, which essentially splits in 2 steps. We evaluate the current policy, estimating the value function that this policy is inducing. And then we iterate on we improve the policy. So for example, by choosing the action that is the best according to the value function estimate. And today we actually look at unknown Markov decision processes. So if you do not know the dynamics of your system, the transition probabilities, then comes the question, can we still estimate the value function if we don't have these quantities, or just using episodes, so trajectories of your system? And the answer is yes. And actually the methods that you will see today are kind of the columns on which, like the fundamental columns on which a lot of reinforcement learning is built. So really understanding what's going on, I think is good. So yeah, just a recap. So the goal in reinforcement learning here is that you want to estimate the value function under your current policy. And so you have a policy, you run episodes, and you want to know what is the value of each state under following this policy. And the value, again, recall is the expected value of the return in the state, and the return was the accumulated reward. So you sum up rewards and you weight them with this discounting factor gamma. And yeah, why do we need the value function? Because the value is essentially exactly what you want. If you move from one state, taking an action to the next, you get a reward. But how valuable this state is on the long term, that is the sum of rewards. And then we encountered the Bellman equation. If we insert it into the equation above, we end up with this equation. It looks a bit different from the equation you see in Sutton and Bartos' book. But essentially what it's doing is just an expected value. So you have the policy, which is a probability distribution, times this transition probability distribution. So what's the probability taking action A to go from the current state S to the next state S prime? And then you multiply the whole thing with your estimate for the current return. And this estimate is the reward function taking action A at state S plus the discounted value function for the next state. And this recursive equation we will essentially use a lot today. So yeah, in dynamic programming, what we would do is we could just use the fact that we know the probability distribution and the state transition probability distribution and actually compute the value using this recursive definition explicitly. The problem is often we don't have this, and then what do we do? Yeah, we need to estimate the value function from experience. What does it mean? So assume you have any kind of system, for example, a Monopoly game, and you know the rules. So if you're in this state and you do this action, then you know where you end up next. But it's quite tricky and mathematically involved to compute the probabilities to do so. And so what you would do is you would just maybe take random actions. You go through the state of your game, and over time you collect different states with different actions, and you call this an episode. And yeah, so if you collect data in which you want to learn your value function, of course, the elephant in the room is how do you collect the data, right? Because if you always follow one policy, you will never find new states. And so if you don't see the whole state space, how do you know that this is the best value? And this is essentially a fundamental problem in reinforcement learning called the exploitation-exploration trade-off. You can exploit your current policy, but then maybe you miss out on a better policy, or you can explore, for example, using random actions, and maybe you find better options. And to just give you some examples for this, so robot control is one. So you can, let's say I want to grab this pen, and I could do it like this, but I maybe could also do it like this. And the question is, you would not find out what's the best movement if you don't try out different stuff. Another thing is Go or chess. Maybe you know that there's a clever starting position in a game and you try this, but sometimes you just do random stuff to see how the opponent reacts, and then you realize that this was a good move. A very physical example, which I find quite cool, is, of course, if you have a fusion reactor in physics and you have a magnetic field, you could think about, okay, I use the current magnetic field and it works best, produces the most energy, but I could also try to meddle around with the parameters and find a better thing. And that's actually something that reinforcement learning was used for. And one example I personally often encounter is in a restaurant. For me, it's if I buy ice cream, I always ask myself, shall I get just stracciatella? Or do I buy this random ice cream that most likely I don't like, but I nevertheless get it? But then of course, you have new experiences and know how valuable stracciatella is. And so the first message, so this means that if you have sometimes if you talk about these episodic methods right now that collect data, you can, for example, use a random policy to hopefully cover your whole state space. To hopefully get a lot of experience and then get a good value function estimate. Just always reusing the same policy in these methods that we see here now is usually not a good idea. You need diverse data. And maybe the simplest example is, imagine you have a robot arm and you collect 10 hours of data, but the robot arm is not moving. It's just one data point. It's completely not informative about your transition dynamics. And so what you would need to do is like move randomly. And we will see this in lecture 5 in the banded arm problem. That's all about exploration. Yeah? Yeah, of course. I think it was fine. Can anyone hear me? No, everyone? Okay. Okay, so the first method we look at is Monte Carlo estimation. And that's really the maybe easiest thing you can do if you have episodes to estimate the value function. And what we do is that we know the formula for the return is actually the sum of rewards. I think it's here or not. So the value function is the sum of the return is the sum of rewards, discounted rewards. And so if we collect rewards over an episode, we can compute for every state what is the return. Then we have several episodes and we average. The second method we encounter is temporal difference learning. That's similar to dynamic programming, uses the Bellman equation. to do bootstrapping. So from a next value estimate, we estimate the current value estimate. And it uses essentially this equation, but in an altered form. So on both methods essentially just learn data from the state, actions, and rewards. So first of all, Monte Carlo. So Monte Carlo value estimation. So we want to estimate the value function. We could also call it policy evaluation if we get the data running under policy. And so what we do is you have a policy and you now just run it on your system at a random initial state, and you collect some data, some trajectory, or here it's called episode. And this episode consists then of state, action, and rewards at different time steps. And now here comes the question. So the total discounted reward is just the sum of the reward. So the return you experience at time step t is just the sum of all the rewards you experience on the next time steps, which you then also discount with this factor gamma. And so, of course, if you collect a trajectory with rewards, then you can directly compute the return for this time step t. And if you do this for many trajectories, you can compute the mean, the empirical mean over these numerically computed returns. No? So, and we will see an example in practice. So, yeah, so what do you do in practice? So you collect trajectories, you go through every trajectory and compute the return at each time step, no? Just summing up the rewards. And then when you have for every trajectory, you have for every time step a reward, and then you compute the average of these, you compute the average over the returns for every state. And it sounds a bit complicated, but it's not. So maybe it's more intuitive if you see it here. So you have several episodes here called tau. You initialize the number of state visitations. So how often you visit a state that you save. In the beginning, you haven't seen any state. So for the state S, NS is 0. VS, because you want to compute an average, right? So you need to sum up the returns and then divide them by the number how often you saw these returns. No? And so the sum is this VWS. And then what you do is so for every trajectory, you start at a time t, and you first of all say, okay, I visit this state now once, so I increment the counter by 1. Then I compute the return going through the trajectory, right? Accumulating the rewards. Compute the return at this particular time step and state, and add this to the sum of returns I've seen at this state at time t. And then you just, at the end, if you have done this for all your trajectories, you divide the sum of returns by the number of how often you visited the state. And then you get an empirical mean estimate for your value function. And here an example. So the discount factor gamma here is 1. Yeah. This one? You mean this this tau proportional to pi, right? That the trajectories are sampled from your policy. It's a reinforcement learning notation. In the beginning, it's a bit confusing. What it means is that you start at a random state, you run your policy until your episode is finished, and then this one is tau. No? Pi stays the same, yeah, because we do so we compute the value function under this policy. Okay, and so in an example we can roll out so we draw this tau from pi, right? So we apply a policy, and for example, we initialize in this state. And then we do follow our policy. So we walk along here, and for every state transition, we get a -1 reward. And so, yeah. Yep. Yeah.
Why don't you divide by the number or maybe
because we will see it here. So some trajectories don't visit every state. Sorry, some episodes don't visit every state. And what we care about is estimating the return for this particular state. And maybe we visit it twice. And then, of course, we have 2 return estimates, and we divide it by the number of how often we saw the state.
And this is a process.
Yeah, exactly. Yeah, it's also called, this method is actually called every visit MC. So we count, every visit counts into this average. There's also first visit MC, where only the first visit counts. But we decided that this is like a special case. We just do now this every visit MC. And so how does it look like? Yeah, you start at random states. So one time here, one time here. You follow your policy, and you get rewards -1 for every state transition. And now you can use this, the equation for the return, right? So you, what is the value? What is the return at this point? It is the return from the previous state plus the transition reward. And add times gamma, of course, but gamma is 1. And so if you look at it, it's -1, adding in another reward, -2, -3. So it's the current value estimate plus the transition reward. And so you see -1, -2, -3, 4, 5, 6, 7, 8, 9, 10. And we visited, for example, this state here 3 times. And we collect 1 trajectory more. And now the value function is essentially just the mean over these returns. So, for example, in this state, we have -10 and -4 and -6. So this is -20. How often did we visit the state? 3 times. And so it's -6.6. No? Okay. And it's, in Sutton and Barlow, there's an example that I personally do not like so much because I have no idea about blackjack. But if you read up the rules, it's actually not so difficult. So you're the player, and then there's a dealer. And the goal is that you get as close to 21 in the number of card values you have, but not over 21. And so essentially you start, so every card has a value, 1 to 11. The ace can be 11 or 1. You get from the dealer 2 cards, and the dealer has 1 card open and 1 card is not shown. And now you can say, okay, you have 2 actions. You can say, I want to quit. So I'm happy with the card value I have. So maybe the 2 cards I have are a 10 and an ace, so that's 21. Then I directly win. And so I say, I stick, I've won. Or you can say twist. So you get from the dealer another card, and you hope that it increases your value to 21, but not above it. Because what is the reward? Well, if the sum of card values is larger than the dealer cards, and the dealer also gets cards, then you win. It's +1. Then if the card values are the same, the dealer cards and my cards, then the reward is 0. Nothing happens. You don't get the reward. And if your card values are smaller than the dealer values, then you lose. And for the action twist, so if you say, I want to take another card, there's the option that you increase your card value, fine. So nothing happens, there's a reward of 0. Or you go over 21, so you lose. And yeah, so long story short, there's a lot of cards. So essentially ace to 10. You have this in the state, the sum of cards. So we assume we draw cards until we have a value of 12, and then so we have the state from 12 to 21. And we have the state if you have an ace or not. Why? Because the ace is special, it can be counted as a 1 on 11. And so if you look at if you now do Monte Carlo on this game, so we want to, so we essentially we play this game. One implicit is playing until you lose or you win. And here you see the value function estimates for, so this axis here is which card the dealer is showing to you, so which card the dealer has. So here on the left, it's an ace. On here on the right, it's a 10, and these are all the different cards. This axis going into the figure is the current sum that the player has. No? So what is your card value showing? And this row is if you have an ace, and this row if you don't have an ace. And then the column is you train Monte Carlo for 10,000 episodes. So 10,000 times playing with the game of blackjack. And this is 500,000 episodes. And of course, if you, as we will see on the next slide, if we play for a longer time, Monte Carlo converges to a solution. And so this estimated value function, so this is the value you're observing in every state, is getting smoothed out. So it's a better approximation. Maybe interesting is why is, for example, if you have an ace, you see that here this is kind of bumpy, and if you don't have an ace, it's smooth. Do you know why? So why is your value function depending on if you have an ace or not? I'm not asking. It's so the answer is because obviously there's an 1 or 11. So the ace can be used as a 1 or 11. So if you would draw another card and you would go over your 21, then you can say I have an ace, count it as 1, and then you don't lose the game. So there's a higher probability that you don't lose the game. So having an ace, all the states are more valuable. Then why is if the dealer has an ace, do you see that so all these values are kind of constant, but then if the dealer has an ace, then the value function is kind of dropping. And why? Because obviously the dealer has the same advantage. So the dealer also can use the ace as a 1 or 11. And so it reduces his probability of drawing another card and losing the game. And then, of course, because our policy here, remember, we compute here the value function under a policy. So we need to predefine the policy currently that we're using. And the policy here that we are using is we always take another card until we have a card value of 20 or higher. And so this means that if we are in this state space area, the value is not very high because we can essentially mess up the game, right? Like if we draw another card, we can lose. And only if we are in the 20 or 21, close to the player sum, then we know we have won and the value rapidly increases. And now I have a question for you. And that is, so, I mean, we know the game, right? We know the rules of blackjack. And so why don't we use dynamic programming for this? And I give you 3 minutes of time to just talk with your neighbor. Okay, so everybody done? So, okay, so why don't we use dynamic programming? In this example, you could use dynamic programming. You could compute the transition probabilities because we assume what the dealer has. We need to know the whole state. And then you can compute, and essentially, if you draw a card, it's without replacement, and you can figure out what cards are missing and what's the probability to draw a different card. But figuring out the individual probabilities, just in this simple example, is really annoying. It's a lot of math, and you can make mistakes. And yeah, so for robotic systems, it's even more difficult because then you need to know the dynamics. Estimating the dynamics is maybe difficult, and so you like steps that often is assumed in controls that you have the dynamics model is often quite difficult to obtain in practice for many problems. And so of course it's convenient. You can just sample experience, run Monte Carlo, and get the value function that almost looks like too good to be true. Yeah, discuss. Computing probabilities is difficult, and simulating the environment is often easy. Yeah. So and now in Monte Carlo, so far we computed the returns in every state at every time, and then we averaged over we summed up these returns for every state, and the sum we saved in this matrix WS. And of course, this means that we have more memory, right? We have this matrix WS here in the grid world example. Can we live without it? And that's a question I have for you. So essentially, what we're doing here is we compute an empirical mean, right? So we have this mu k, and the x here is the return that we compute through the rollouts, and then we average over the returns we observed in every state. So my question is now, and this is a question for you. Can you compute can you reformulate the mean so that it only depends on the previous mean at the previous iteration of the algorithm, mu k minus 1, and the new observation. So for example, we have a value estimate for state that's now mu k minus 1, and now we observe a new return through the rollout, and we want to add it to the mean. So this is kind of, I'm asking you to reformulate the mean equation as a recursive equation. And yeah, please also like 3 minutes. Okay, so I will just do it on the chalkboard. So UK is of course 1 over k equals 1 x times I to k. And now we can just pull out, sorry, it's k, sum I equals 1 to k minus 1, xi. And then, of course, what is the mean for k minus 1 samples? And this is so you add k minus 1, sum xi. So this term here is mu k minus 1. And then you have, sorry, this is of course plus. And then plus xk times 1 over k. And then you can multiply it out. And what you get, so yeah, so again, what do? We pull out the last k, that's the last update, yet in our case. Then we write k minus 1 divided by k minus 1, so we are just adding identity here. And then this part is the mean, v k minus 1 times k minus 1. We multiply this thing out, and what we get is this equation. So the next mean at iteration k is the previous mean at k minus 1 plus xk minus mu k minus 1 divided by 1 over k. And so this means that we can now rewrite the MC algorithm we saw and make it incremental. And so every time we get a new episode, we compute the returns. And now we can incrementally just update our value estimate. So this was the mean at the time step k minus 1, iteration k minus 1. We get the new return. And then this is exactly the formula that we just derived. An alternative of this algorithm is that if your Markov decision process changes over time, then you can have a forgetting factor alpha for this term here. And so that your value function slowly goes, if nothing happens, resorts back to where it has been before. And now comes the alternative, and that's temporal difference learning. And that is, so again, we want to learn a value function. It's the same setting under policy. So we run a policy, we get experience, we get episodes, tau, it's the same. And we want to update the value. How do we do this? So in TD0, that's the simplest algorithm for temporal difference learning, we essentially use an changed version of the Bellman equation. So if you look at this is essentially remember that your return is now replaced by this estimate, and that is RT plus 1 plus gamma over VST plus 1. And so First of all, let's understand the high level structure of this algorithm. And it looks a bit, if you have worked with gradient descent, that you have your current estimate, then you have a step size, and then you have the change. Here it's called TD error. It could be in gradient descent, it would be gradient. It changed that you now change your estimate. And in this TD error, you have a target. So you have a current value function estimate. Yeah? So this is your value function at this state, at this time. And now you have a direction in which you want to update, in which you want to pull the value function. And that's exactly this term that comes from the Bellman equation. So if we compare temporal difference learning to Monte Carlo, then we see that the structures are actually pretty similar. So you have the current value function estimate, you have, and then you add to it this an error. In Monte Carlo, it's this return you compute from the episodes. In TD learning, it's just the next time reward plus your current value function estimate. And the value function estimate that the next state had in the current iteration. And then, of course, both are multiplied with the step size. So usually in practice, you could run this algorithm just on one episode and then always update your value function. In practice, what you do is you take a batch of trajectories, compute the updates for every sorry, not trajectory, episodes. You compute a bunch of episodes, a batch, and compute the update for each of these episodes for every state, and then you average over these updates. And let's look at an example. And so this is also in Sutton Barton. If you want to read later, there's also an explanation of this. It's an A-B example. So this is how the graph looks like. You have a state A and you have a state B. The transition probabilities going from A to B is 100%. From B to this terminal state is 25%, and here 75%. And the reward here is 0, here 1, and here 0. And what you do now is you collected 8 episodes of experience. So the first episode you start in A, you move over to B, and then the episode terminates. In the second episode you start in B, you observe a reward of 1, and the episode terminates, and so on. So you have these 8 episodes. And now the question is, what is the value of A and the value of B? And let's compute this together. So these are already the values. For MC, it's 0 and 3/4. And how you do this is essentially I put in the upper right corner the equations for what's called constant alpha MC and TD0. That's the two methods we saw until now. And so we call that for MC, we can compute the return for every episode just by accumulating the rewards together with the discount factor, which in this case, no discounting means a discount factor of 1. And so to compute the return starting from the terminal state, we just go backwards and accumulate the rewards. So the return is here just the reward of 1, and then going from this terminal state, you get a reward of 0, and so the return here is either 1 or 0, and then you sum up the rewards, the returns for the state B, and divide by the number of state visitations. And so in this case, you visit this state B 8 times, and you observed a return of 6. So 6 divided by 8 is 3/4. That's the value for B. And I really recommend that you do this at home, just as practice. But I think also we do this today in the exercise, so maybe it's fine. And then the same story, you move onwards and you take the return here. The return for the return you estimate in the first iteration of the algorithm, and you add the reward, and this is actually a value of 0. And then for temporal difference learning, you use this equation. So you initialize your value function in every state to be 0 in the first iteration of the algorithm. And then so you start here at this state t, and your so the value here vs of t is 0. Then you look at the next time step. What's the value? At the first iteration of the algorithm, it's 0. And what is the reward you get for transitioning RT plus 1? In this case, it's 0. So VA is it's 3/4, right? Okay, because you go backwards and you use the previous you use the previous value estimate. And so it really depends in which direction you go and how exactly you implement the algorithm. One important conclusion here is that MC and TD converge to different solutions, and we will get back to this in a couple of slides. Let's look at another example, and that's the grid world. So again, we have these trajectories, but if you do batch temporal difference learning, typically what you do is you don't use an episode once, but you can repeatedly use episodes. So because the problem is TD takes a bit time until it converges. And then, so you can first collect one episode. So again, the transition probabilities is -1. And that's why the value, so this is the value function estimate, is also -1 in the beginning, because RT plus 1 is -1, and the next value function is 0 in the beginning. And but then if you repeat this algorithm for several iterations, like in this case 6, you see that there's the value function is converging to a solution. And this looks similar to what we've seen in Monte Carlo, but it's different when we have several trajectories. So again, in this batch version, we do the value function, this temporal difference value function estimation for each trajectory. So these are the yellow values. And then we compute the mean of these values to get the value function estimate. So in this case, we have this one trajectory where we got -1, -2, -3, and the other one where we got -1, -2, -3, -4, -5. So this was running TD on this episode. And then we take these two values from the different episodes and we compute the mean. And that's why we get -4 here. And we can do this with another trajectory. So here, this trajectory gives you a value at this state for -2. And this trajectory here, you got a value of -9. So again, you average over them and get -5. Yeah, so what you maybe see is that the algorithm uses intermediate values. We will see this in also in a couple of slides. Okay, and so another example, in this example, I think it's also from Sutton and Bartow, and it's really confusing. Like, and I think it's by purpose, because it really forces you to test your understanding. Like if you understand this example, then it helps you a bit to abstract reinforcement learning on different problem settings. So what's this problem? You start so you want to drive home, and you want to estimate the predicted total time to drive home. So to do this, you go to certain states while driving home. So you leave your office, you go to your car, it's raining, that's a state. You exit the highway, you see you're behind a truck, you drive onto the home street and drive home. And so at every point, at every state while you're driving home, you are essentially, of course, have the elapsed time, and you predict how much time you need to go. So essentially, you're predicting the total time, right? Because the time that passed plus the time you predict you need to get home is the time you predict now is the time you will take in total to drive home. And so if we look at the value function here, the return you're trying to estimate with the value function is the predicted total travel time. And of course, if we at every state we move on, in the state, and we change now our prediction for the predicted total travel time, essentially predicting the time to go. And so this looks really confusing in the beginning because you're thinking, where's the value function and where's the reward? Or where's the return and where's the reward? And so the return is the predicted total time. And the reward is essentially how much your prediction changes from state to state. So if you're constant, if your prediction remains kind of constant, then this is a reward of 0. And then what temporal difference learning is doing, there's this empirical mean and it tries to pull the value estimates towards the empirical mean. So that's why you have this value estimate. While you're leaving the office, you're saying, I'm home in 30 minutes. But when you did this rollout, you computed, okay, the return actually was in the mean 43, and then you try to pull your value estimate over. And temporal difference learning is fundamentally different. That actually you just look one step ahead, look at what is my current value estimate at, yeah?
Learning and MC, the word retrieval learning. But in this example, because they're using different methodologies, but their answers are quite the same. So is EG0 equivalent to time t given the equation?
And it's a good question. We get to this. Yeah. And no. So here, essentially, you just have this relative pulling. So you just look at your current state, and then you have this smoothing effect over time. The problem with that is that the smoothing can take a lot of time, a lot of algorithm iterations. And so, first of all, before we answer the question, what are these two algorithms converging to, is how does the estimate look like in general? And I'm just throwing this onto the slides without explaining you why. I hope you forgive me. And that is that. So the return in general is an unbiased estimate of the value function of a policy. So there's this value that a policy has, and computing the actual return, it's an unbiased estimate. And the 2TD target. So if you use the Bellman equation to add the reward as the next time step plus the value of the real policy at the next time step, then it's also an unbiased estimate. The TD target is replacing the true value function with your estimate of the value function. And this is biased by your estimate. So we just replace here V pi by V. And what this means in practice is that Monte Carlo is eventually converging to this two return, the two return, like an unbiased estimate. But the problem is that over the course of computing the return through Monte Carlo, you have these several rollouts that you add together, and all this noise and uncertainty in your policy is adding up, and that increases the variance of your estimate. And in practice, this means that you need a lot of samples. Like we saw there this example with 10,000 episodes. While temporal difference learning, the variance is lower, but because it's biased, you might not converge to this exact mean estimate. Yeah, and then there's maybe also how you apply this method. So Monte Carlo, because you need the whole episode and then compute the return backwards, you need to wait until the episode finish. So it's an episodic algorithm, while TD, you in principle can just collect a new state and then directly update your value function. So you can update your value function online. And so TD0 converges eventually to V pi. This is discussed in much more ample detail in Sutton Barto. But yeah, it takes also a lot of time. And TD0 is really sensitive to initial conditions. So if you initialize your value function to 0, it might take a lot of time until the individual values are being pulled up starting from the terminal state. Like it really needs time until it propagates. So Monte Carlo is not so sensitive to the initial condition. And first of all, why people use Monte Carlo is that it's really easy to use and implement. It's just randomly sampling episodes and computing the average. One more example before we do a break. And that's the random walk example. So you have this Markov decision process where you start at the state C. Then there's a states, there are two terminal states. You never get a reward except of going right. Then you get a reward of 1. And the policy you do is a random walk. So every time you have a 50-50 chance, or you choose the action 50-50 going right or left. And now we want to know what is the value function of this random walk policy on this example. And so we use TD0 with a step size alpha value of 0.1. And so what you see here is the x-axis are the states. So in which state are you in? And the y-axis is the value function estimate. The black line here is the true value function, which you can compute because you, of course, know the Markov decision process. And here, this numbers is the number of algorithm iterations. So in the beginning, you initialize your value function to 0. And then after 100 iterations, you converge to almost a true estimate. But to note, even if you increase the iterations, it really slowly converges. Like after 100 iterations, you get here, but then you need much, much more iterations. And also, if we look at the learning curve, so if we take the root mean square error between the true value function and our estimate, and we compare TD to MC at different values of alpha, then we can see that there's alpha is essentially a tuning parameter, and there's a point where we go eventually where the root mean square error reduces over the number of episodes and then increases again. So here alpha 0.05 seems like a good value, but it takes a bit more time to go down. And TD performs here better than Markov, Monte Carlo methods. And now to your question of where do these algorithms converge to? So Monte Carlo simply converges to the minimum squared error between your value function estimate here V. It's essentially over time converges towards the actual return in a way that it minimizes the mean squared error. That's a mean squared error estimate. And this is very different to TD0, because TD0, this looks hella confusing, but essentially it's that TD0, it's the value function implicitly defines the underlying Markov decision process. And the value function is chosen in a way that the maximum likelihood of this underlying Markov model is being maximized. So you're maximizing the likelihood that these transitions occur, like if you would follow the value function. And so what this here means is just this 1 is an indicator function. So it's 1 if this condition here is 2. And so you're estimating the state transition probabilities going from state S to the next state S prime under action A, essentially by just counting the number of transitions and dividing by how often you saw this transition. It's like an empirical estimate of the probability on how likely it is that you do these transitions. And this is what TD0 is converging to. And the reward function estimate then is essentially the same thing, just where you take the reward that you observe at this transition and then also have divided by the number of how often you encounter this reward at this state transition. And these are different estimates. That's important. It's essentially two correct answers to the same question. And sometimes, because temporal difference learning exploits the Markov property, that's how I see it. That's why it's more efficient, it's converging much faster on if you have a Markov process. But MC, because it doesn't have the assumption of that the state is Markovian, you just use the formula for the returns. There's no assumption that this returns are obtained from a Markovian process. It also works on non-Markov systems. And this can be quite handy because you have this method that's very easy to implement. And you don't need to check if your system is Markov. And so, okay, the last slide before we do a small break. So in the previous lecture, we saw dynamic programming. Then we talked about Monte Carlo. where we essentially do a whole episode and then compute the returns. And temporal difference learning is kind of in between those two, because on one hand, you use bootstrapping, like in dynamic programming. You use an estimate of the value, your value function estimate at the next time step to compute your current estimate. And in dynamic programming, it's the same. But unlike dynamic programming, you are not explicitly evaluating this expected value, but you are using this empirical mean equation, especially in batch TD learning, to estimate the value function. So it's a combination of bootstrapping and mean estimation through data. Okay, then let's do a 5-minute break and then continue.
I had a question to
Yes.
like before where we had this AB game,
Which one?
the AB example,
Let me.
and the temporal difference learning.
Okay, I quickly have to. I'm a bit worried that my Zoom is. Okay. Let's wait for 2 minutes. So, okay, so now we got to know the basic version of Monte Carlo. We got to know Monte Carlo value estimation. We got TD0, the basic version of temporal difference learning. And now let's, of course, address the elephant in the room. Can you extend these methods? And one very simple extension is actually doing n-step temporal difference learning, n-step TD, which is kind of it's smoothly transitioning between TD0 and Monte Carlo. What do I mean by this? So the idea is that if you look at the function for the return, right? The return over an episode is the accumulated reward. So you sum up the rewards and weight them by gamma. And in temporal difference learning, you said, okay, I get the reward at the next time step t+1, and all the rest using the Bellman equation, I replace by my value function estimate. But why not compute the return using several of the rewards I've observed for several time steps into the future, to say so n steps, and then the rest, again, using this recursive relationship of the Bellman equation, you replace by your value function estimate. And that's exactly what n-step TD learning does. And why is it Monte Carlo on one extreme and TD0 on the other? Well, if n equals the number of the absolute length of the episode t, like if in worst case, if the length is infinitely long, then this equation is just the normal function for the return as we used it in MC. So the algorithm reduces to Monte Carlo value estimation. And if n equals 1, so if I just look one step ahead, and then the rest is estimated by the next state, the value estimate of the next state, then it's simply TD0. Why would you like to do this? So the main reason is that if you compute the value function only, like the update for the value function only for using the next value function estimate, then it takes a lot of time until you pull all these value functions towards the optimal solution. And if you can sum up over several reward functions, the algorithm might converge a bit faster. And we will see this on the next slide. So this is again the random walk example we just saw before the break. Now, recall, I can go right or left, and only if I go several steps to the right, I get a reward of 1. And the policy I'm trying to estimate the value of is the random walk. And so the x-axis here is the alpha value. So this is the step size of my update with which I update the value function. And the y-axis is again the root mean square error. So the error, the distance to the true value function. And so I run this algorithm and I look at different versions of n. So n 500, if n is 512, so this is the one extreme that's essentially doing Monte Carlo, doing the whole rollout, and then just computing the return, going through summing up all the rewards and averaging over them. And n equals 1 is the other extreme, that's TD0. So I just look at the next reward and the next value function estimate to update my current value function. And what you see is that there's a trade-off. So there's a n equals 2 or n equals 4 that seem to optimize this problem, to be the most accurate depiction of this value function that is induced by this policy. And of course, it not only depends on n, it also depends on the step size alpha. And so now there's an extension on top of the extension. So we now got to know this n-step TD learning. Now we move on and ask ourselves, well, why don't we do several different n-step predictions? So let's say TD0 is having n equals 1, right? And I get a value function estimate. TD2 is is summing up the rewards of 2 steps, and then is taking the value function estimate at this t plus 2. And then you have maybe t, now what is the index here? Capital T, so this is essentially the length of the episode. This is Monte Carlo in the extreme. So you just sum up the rewards to get the return. And so if I have these different value function estimates and they're all good in their own way, then an idea is, can I just sum them up, compute the mean over it? And TD lambda is doing something slightly different. It's weighting. So it's computing the return you get for different TDNs, for different n values. So you estimate the returns as described on the previous slide with this n-step look ahead. But now these returns are weighted by lambda to the power of n minus 1. And then also 1 minus lambda. And you might be wondering why this weird scaling. And first of all, lambda is always smaller than 1. So if n gets bigger, then this weighting gets smaller. So you weight the TD0 step where you estimate the most, return estimates the most. And then as more n's you look into the future, this return estimate gets smaller. And we see it on the next slide. So here time is essentially here the n factor. So how many steps you look into the future, and then takes the current value estimate. And this shows you here the weighting. So for n equals 1, you have lambda to the power of 0, so it's 1, so it's 1 minus lambda. And then it exponentially decays. And this function is chosen in a way that the sum of all these returns adds to 1. Like the returns, of course, don't add to 1, but the weighting of the returns. And that somehow makes intuitive sense, right? Like it's, of course, pretty heuristic, but it makes sense. You have different estimates for the return. No? You look different number of steps into the future. It's a slightly different algorithm. And now you have these estimates and you want to sum them up. But when you sum them up, you want to make sure that all of these estimates add to 1. And because you have this weighting, you make sure that short-term predictions are a bit more weighted. And how you usually compute this, so there are two ways, is one is you start at you have your episode and you start at the beginning of your episode and you look into the future. And of course, this is only possible if you have collected the episode already, right? Like I need to collect the whole episode to then be able to look at everything I saw in the future. This is called the forward view. And the forward view, this is essentially, it's the easiest thing you can do because it's quite intuitive to look forward and just collect an episode. And the alternative is the backward view. So you have now a latent variable, and I already apologize for the way how I pronounce this word, eligibility trace, ZT. So you have an extra variable at the state that it should encode the value of the state estimates in the past, and we will get to that. And so here's another comparison of here's a comparison of actually TD lambda and n-step TD that we saw before. So it's the same plot as we just saw 2 slides ago. But now by TD lambda, we can change the lambda value. So again, it's a value smaller than 1. And for n-step, we change the n value and here also look at the step size. And what we see is that both kind of have a trade-off for the right hyperparameter lambda or n. In this example, there's no clear performance difference, I would say. Yeah. Maybe one interesting fun fact is that TD lambda, so if you insert lambda equals 0, then only the current state is updated. And essentially what you get is TD 0. So lambda equals 0, that's again, we're getting TD 0. But if you change lambda, then it's kind of an averaging over n-step methods. And what you can show is, and this is a bit more complicated than this transitioning on the end, like n-step TD, that was pretty clear why one is MC and the other one is TD0. For lambda equals 1, actually for the offline, if in this case, it's a bit more intricate. But what you can derive is that if you do offline updates, so you collect the whole episodes into the update, then TD1 is the same. The update is the same as updating using Monte Carlo. And yeah, and then forward view or backward view. So the forward view is you collect the episode, you start at T, look into the future, and then do these n-step predictions to compute the returns over which you compute then this weighted sum. In backward view, you can actually do this online updates using these eligibility traces. And we will actually in this lecture not talk about it so much. Sutton and Bartow has a whole chapter on this. I think it's chapter 9 or 8. It's relatively late in the book. And the reason is that until 10 years ago, eligibility traces was actually a big thing in reinforcement learning. Nowadays, with deep learning methods often being used, we anyway do offline updates. So we collect experience, we save it in a buffer, and then we update our value function by sampling from this buffer of past experience. So it's an episodic. The way we use it nowadays is usually updating values offline from episodes. But nevertheless, eligibility traces is a really mathematically beautiful idea. And I really recommend that you read this chapter because I think it's cool. You should check it out. And so just on a very high level, what's the idea of eligibility traces? The idea comes actually from the early beginnings of reinforcement learning, when people did neuroscience on animals, and they were wondering, let's say you give some animal an electric shock, and before it was the 50s, and so you ring a bell 3 times, and then flash a light, and then the animal gets the shock. And then, of course, this is a credit assignment problem. The animal will think, was it the bell or was it the light that I got a shock from? And this is also true for humans, that how do we value experiences? It seems there are two important factors or ways on how you estimate value. One is the frequency with which we observe events, certain states and actions. And the other one is, of course, how recent was it? How much in time? Because if something is really 1 month ago, it's mostly not correlated with what I'm experiencing right now. Or maybe this. And so the idea of eligibility traces is kind of a heuristic to store this information in this vector that is updated at every time step and is traveling with you and is saving the information you've seen until now. And so how do you implement it? So you have this. We call that, for example, if you're in the grid world, you have your value function estimate is essentially a matrix, so a value for every state in the grid. And now you have, in addition, also an eligibility trace matrix, and it's the same size. So for every state, you have an eligibility trace. And then you essentially do TD learning, but you scale it by this trace, this heuristic that tells you how important this update is. And so this is how it looks like. So again, you have this TD error as we saw before in TD learning, TD0. But now you have this eligibility trace that you updated alongside, that you use to weight the update, but that you also change. And that's yeah. And again, this is talking about offline and online updates. So yeah, you can offline means that you do the method, you collect the experience, the episodes, and then after you collected all episodes, you update your value function. Online, and an interesting fun fact. So if you do these updates offline, then the sum of offline updates, both for forward view and backward view TD lambda is the same, but this is not the case if you do online updates. So so the backward view is essentially using the eligibility traces, and the forward view is it's using the equations we have seen in this lecture. And so now online updates TD lambda is so forward and backward view TD lambda are a bit different. And this is a nice exercise. As I said, if you do this chapter on eligibility traces, it really tests your understanding on these experience, these TD and MC methods. So we skip these slides. This is just for self-study. And then in the end, you arrive at this table where you separate the different algorithms in offline and online updates. So you first collect data or not. And then in how you compute the updates in a backward view or forward view manner. And then you see that for certain lambda parameters, certain methods arrive at the same solution. And for online, this is not necessarily the case. And then the final way on how to distinguish the methods is that you can, on one hand, look at the length of the update, right? N steps ahead predictions. So the length of the updates, n equals 1, that's TD0. The length of the updates is infinite or until the state terminates. That's Monte Carlo. In between, we have n-step methods. Then we can look at the width of the update. If we only look at one next state, then we are at TD. But if we look at all next states, then we are at dynamic programming, where we exactly compute the mean. And then there's exhaustive search, which we haven't talked about, which is in between Monte Carlo and dynamic programming. So, and now let's sum things up. So value function estimation is central to reinforcement learning. And this is really this is true. So nowadays, many algorithms in robotics actually are based on these ideas. Of course, there are also other ideas that we will learn in this lecture and the next lectures. But value function estimation is really useful. it's not necessarily trivial because we don't know the random process, and we also have to solve the exploration problem. That is, what kind of policy are we testing, right? And then how we updating the policy. And we learned to estimate the value of a policy of the MDP under policy. We have Monte Carlo, which has high variance but no bias. And it's very simple to use because you just need to implement a simulation of your game and then run different runs with different initial states. And we have temporal difference learning, which has a high variance. Temporal difference learning has a low variance but some bias. And it's if your process is a Markov decision process, it's more efficient. It iterates faster. Then we looked at the combination of both, which is this n-step TD learning. And we saw that small values of n speed up convergence. And we looked at TD lambda, which was actually, it's a pretty old method, one of the early works on reinforcement learning, which is a weighted version of all n-step returns. And there we looked at eligibility traces, briefly discussed eligibility traces. So how we compute the updates, either by looking forward into the future or backward. One we could use for online learning. The other one we can only do offline learning. And that's it for today. And thank you very much. If you have questions, you can just come to the front. I just need to.
Yeah, sure.
Yeah.